Okay, so let's look at some equilibrium constant math, is I think the way it's usually called. And that is how you can manipulate reactions and how it changes the equilibrium constant. So, for example, let's say I have a reaction A plus B, right? Well, let's do something simpler. Just say A goes to 2B, like this. Well, the K for that will be equal to B squared over A, right? But what if I doubled that reaction? Well, then that would be equal to 2A goes to 4B. So what does that do? So I'll call this K1 and this call K2. Um, what does that do to the equilibrium constant? Well, that's just going to be B to the fourth over A squared. Now, how is K2 related to K1? Well, if you double a reaction or multiply it by a value, for example, but in this case it's double a reaction, what ends up happening is that's actually equal to K1. It's the original equilibrium constant squared. Basically, you're doubling all the coefficients, so that's the effect of squaring the equilibrium constant. Now, if I had two reactions, right, and I was adding them together to get an overall reaction, so I have reaction one and reaction two, like we did with the rate laws, for example. Um, but if I had two reactions, I was adding them together. So let's say it's A goes to B, and then I have B goes to C, and I add those together, right? Overall, that's just A goes to C, because the B's will cancel out like the intermediates did going from one reaction to another. Well, this equilibrium constant is just B over A. This equilibrium constant is C over B. And again, I'll call this K1 and K2. The net equilibrium constant for this reaction, K net, will be this. It's going to be B over A times C over B, and that's just going to be C over A. So when you double a reaction, you square K. When you add two reactions, you multiply. If you can subtract a reaction out, as possible, then what ends up happening is you end up dividing. But the math it's a lot like logs. If you add two things, it's the multiplication of the values. If you divide two things, it's like subtracting the reactions, that kind of thing. So there's that sort of kind of relationship going on. Now, when you reverse a reaction, and these are common manipulations that we do, right? Then if you had A goes to B, and then you write the reaction as an equilibrium as B goes to A, it's really you take the inverse of K. So this would be K is equal to B over A, but this would be K is equal to A over B. Now, what I really want to emphasize in all of this, though, is that even though we're like manipulating equations and we're getting different numbers out, right? The reaction doesn't care that we're doing that. It will still reach the same equilibrium concentrations regardless of what we do with the equations outside of the solution. The reason we have to do this, right, is so that when we do our calculations, we get the same answer regardless of how we're expressing the equilibrium and its constant. This is just a more complicated example where I have these two reactions with their equilibrium constants. And if I add these two together, these will cancel, right? And then what I end up getting is this overall reaction. That's the equilibrium constant that you're seeing here. But that's the same as if I multiplied these two equilibrium constants together. So this is actually K1 times K2. And you can go and verify that. I did a simple version because it's easier to see, but you could verify that that's the case. So let's practice this a little bit. Um, the following reaction has an equilibrium constant Kc of 3.92 at 1200 degrees Kelvin, right? What is the equilibrium constant for the reaction that's shown below? Now, what you have to do is you have to figure out what the relationship is. And so since the reactants are still both on the same side, but it looks like the coefficients are doubled, right? Then that means this K value, so we'll call this KC1, KC2 for this reaction would simply be KC1, and since it's double, we would square it, right? So that would be the same as 3.92 squared, which comes out to 15.4, like. So I thought I'd do one more example. Let's say you have these two reactions and you wanted to know what the new equilibrium constant was. And you can look at these two reactions, add them up, and get a net reaction. But K net is going to be, right, K, let's call this 1 and 2, Kp1 times Kp2. And so that ends up being, pulling out my fancy dancy calculator, 1.85 times 9.85, and that comes out to 18.2. The overall reaction for this one, the D's would cancel out, and one of the B's would cancel out, and what you end up with is A plus E creates 2C. Oh, A plus E plus B, sorry, I left one out, makes 2C. And then this would be the equilibrium constant. And then you would also be able to write the expression for that. So K would be C squared over A times E times B, like that.